The floor is yours.
All right, thank you. I would like to thank the organizers first for inviting me to this workshop. It really is a pleasure to be in the community of people who are interested in auto-equilibrium behavior of correlated quantum systems. So today I will describe some experiments on correlated two-dimensional electron systems that exhibit the types of far from equilibrium behavior that has not been discussed so far in this workshop. We have been working on this topic for many years, and we are grateful to the NSF and the Magnet Lab for their support. So, as we all know, most systems in nature are far from equilibrium, and many phenomena exist only under far from equilibrium conditions. So, in other words, the far from equilibrium behavior, I need to touch this again, sorry. The far from equilibrium behavior is ubiquitous. So we may ask, how do systems end up in this regime? So one way, of course, is if we supply them with energy. And as we've heard already in several talks in this workshop, including yesterday, this results in transient behaviors, ultra short timescales, and also leads to non-equilibrium steady states. The other way, however, there is a class of systems that remain trapped in states that are far from equilibrium, and thermal energy that is supplied by their surroundings is insufficient to allow them to equilibrate on experimental timescales. And this is why they retain a memory of the preparation conditions for a long time. And the best known examples are glasses or various soft materials as shown here. In this workshop, we have already heard a number of talks on driven systems, but we, in contrast, want to focus on this other group of materials that remain trapped in states that are far from equilibrium. We are interested in the behavior of electrons, so you may ask, like, why do we care about this? Well, as we know, quantum materials are characterized by the presence of many competing degrees of freedom. So in general, you expect that this would lead to the emergence of many metastable states and therefore breaking of ergodicity and the associated non-equilibrium dynamics, such as glassiness. And also, as we heard yesterday in Matteo's talk, there is a lot of research effort out there to not just access those such metastable states, but also to control them and manipulate them for some new functionalities. In recent years, 15 or 20 years or so, there has been a lot of interest also in quantum many-body systems that are well isolated from the environment, from a thermal bath. So the question there is, what happens if you prepare such a system far from equilibrium and let it evolve under its intrinsic quantum dynamics? What happens at long times? Does it reach thermal equilibrium or not? Because if it doesn't, it can retain some memory of the initial quantum state, and this is useful for various applications in quantum information science. So these are the topics, the questions we have been working on for a number of years, and the field really is, I think, at the intersection of condensed matter physics, statistical physics, and quantum information science. So quantum materials, as I already said, are very complicated because they have many competing degrees of freedom. So if you want to study a complex phenomena such as far from equilibrium dynamics, it is desirable to study it in a system that is as simple as possible. So this is why we have been studying a model 2D electron system in which electrons, of course, interact with the Coulomb interaction, and they move in the presence of a random potential due to impurities, defects that are unavoidable in any real material. And we have been studying far from equilibrium behavior using time-resolved or time-dependent DC conductivity measurements, as you will see. So we are interested really in a regime that is far from equilibrium, which cannot be described using perturbative approaches, and where fluctuation dissipation theorem does not work. So to characterize the system, one needs to probe both the response of the system to an external perturbation and fluctuations, which give information about correlations. So in our studies, we have performed various protocols to study both the response and the fluctuations, but in this talk, I will focus only on one particular protocol that probes the response of the system to an external perturbation. And you will see that even such a simple system exhibits very complex behaviors when it's far from equilibrium. Depending on the range of the Coulomb interaction, it can exhibit a glassy behavior or many body localization. MBL is seen, as you will see, when the system is well isolated from the thermal bath. More recently, there is interest in that community, not just in isolated quantum many-body system. They moved on to open quantum systems. So in the last part of the talk, I want to show you some very recent, as of just like now, very recent unpublished data where we studied a system that exhibits MBL, but it is now open. So we do not, I will show you the main results. We do not understand them fully. We are still analyzing some aspects. So I'll look forward to any comments you may have, questions. Yes.
So just to make sure I stay on track, many body localization, you mean something that localization that comes about not due to disorder, but to some.
I will explain. Yeah, just in a few more slides. Yeah. Okay, so at the end of the talk, I will, of course, summarize the main results and outline some possible directions for future research. Yes.
I'm just a bit confused by time-resolved DC conductivity. Is this in contradiction with determinism?
No, you just measure it as a function of time. You start the measurement and go away, and you keep measuring.
I see.
Okay. All right. So, as I already said, the best known example of systems that are trapped in states far from equilibrium are glasses, and everybody's familiar with structural glasses, such as window glass. So these are basically liquids which are cooled very rapidly, such that they are not able to reach the lowest energy state, which is that of a crystal, but instead they get stuck in the atoms get stuck in some random configurations. And as you cool such a liquid down, you can see, you can see that the viscosity of these liquids shoots up by 16 orders of magnitude. So they become extremely viscous. This is why you cannot see them flow. Another well-known example are spin glasses, which are alloys in which a relatively small percentage of magnetic ions, such as atoms such as manganese and iron, are mixed randomly in a lattice of good metals like copper and gold. But because of the random distribution, they are not able to order, so they get stuck again in random configurations or a metastable state. So what is striking about glasses to me is that their phenomenology is very similar, even though obviously the microscopic mechanisms that underlie their dynamics is very different. So this was a difficult problem to solve for many years. It turns out that what all glasses have in common is frustration, which leads to this rugged free energy landscape where each minimum represents one metastable state corresponding to a particular configuration in the system. And these metastable states are separated by energy barriers with a wide distribution of heights and therefore relaxation times. So when the system transitions from one metastable state to another, this involves collective rearrangements of the system. So the configuration is different. So because of this wide distribution of barrier heights, these are slow processes. And so on experimental timescales, the system can probe a relatively small number of states. It cannot probe this entire landscape. And this is why the system is ergodic and it exhibits non-equilibrium behavior. So the problem of the mathematical formalisms to describe glasses was, after several decades, formulated by Giorgio Parisi in the context of speed glasses, but this was later had a huge impact on other areas of science like neuroscience, machine learning, biology, mathematics, and so on. So in that picture, these metastable states have this hierarchical or tree-like distribution. And moving on, okay, now what about electrons? We are interested in electrons, can exhibit glassy behavior. The answer is yes. And so we are interested in the regime where potential energy exceeds kinetic energy. And last week, Ilya introduced this parameter RS, which is a ratio of the average Coulomb energy per electron to Fermi energy or kinetic energy. And in 2D systems, this increases the relative importance of interactions, increases as we reduce the density. So we are interested in a low density regime. And if we had only Coulomb interaction, obviously the repulsion would favor a uniform distribution of electrons. But if you have only disorder, this would favor a non-uniform density distribution. So if you have both of these present, what is the system going to do? Obviously, it cannot satisfy both requirements. It gets frustrated. And it was shown numerically decades ago that this gives rise to exponentially many metastable states with similar free energy, and this was termed the Coulomb glass. So Coulomb glasses exhibit, as I said, and as you will see later, similar phenomenology to other glasses, such as spin glasses. For example, they exhibit dynamical heterogeneity, and this was obtained using the classical Monte Carlo. What this shows are trajectories of individual electrons within a given interval of time. So each color is a trajectory of a different electron. So you can see that within this, yes.
Can you tell? So you didn't mention the Wigner crystal, but you see, the very simple naive question is that if RS is large in a clean system, you will have a Wigner crystal. In a disordered state, so you have this fluid to glass transition.
Yeah.
Is there any knowledge about if this glassy state of electrons appears that RS is much lower than the threshold for Wigner crystallization?
No, this is RS is relatively small, and as you probably know, it's been a challenge to actually observe Wigner crystal trees in the system. I'll be discussing.
Is there any
So in this, I will show you. So we have obviously results. This is what I'm talking about. This on glassy dynamics. So RS is maybe 4, and
so it's much smaller.
Oh yeah, much smaller. Yeah. So these Coulomb glasses exhibit, for example, dynamical heterogeneity. So within this time period, you can see some electrons can move all over the place, but others remain trapped. So you have regions of fast and slow motion. But if you look at some later times, this picture will change. So there are fluctuations both space and time. It's heterogeneous. Okay, so moving on to the quantum many-body systems that are well isolated from the environment, what happens at long times when they're prepared far from equilibrium. As we all know, most systems in nature are thermalizing, they reach equilibrium, and this happens because different parts of the system can exchange particles and energy. And in this process, the information that was encoded in the initial quantum state is lost with time, and eventually the system is described by only a few global conserved quantities. So the interest in recent years has been trying to find mechanisms that lead to the failure of thermalization. Because if thermalization fails, then some information about this initial quantum state can be retained at long times, and we can use it, say, for quantum memory. So indeed, several mechanisms that break ergodicity have been identified. Most of them are fragile, which means that this non-ergodicity happens only for some special parameters under very special conditions, which are probably which are difficult to achieve, I think, experimentally. The only known robust mechanism for breaking of ergodicity, for failure of thermalization in isolated system, is the many-body localization. And it is called this way because it was developed as an extension of the well-known Anderson localization for single particles in a strong random potential to interacting systems. So in Anderson localization, the wave functions are exponentially decaying. There is no transport, so this is why system cannot exchange particles or energy, and this is why the system is non-ergodic. So the idea was, okay, can this property of non-ergodicity be retained if we add some interactions to this quantum many-body system? And it was shown that indeed for sufficiently short-range interactions, this non-ergodicity is retained. This is why it's called many-body localization. But it was shown later that you can observe similar behavior in systems, I think, with quasi-periodic potentials. But we will be focusing on disorder systems. So you need a strong enough disorder, first of all, and short enough interactions. So as I said, a lot of people have been working on this, especially theorists. These are some key questions that have been under debate and some still are open. For example, it was believed for a long time that you could see that a true MBL phase could exist only one-dimensional system. So the two-dimensional systems were under question, and we are studying a 2D system. More recently, there was debate about this, but I think consensus has been reached, but true MBL phase cannot exist even in 1D. And what do I mean by true MBL? I mean in the thermodynamic limit at infinitely long times. But there is a consensus that there is a pre-thermal or MBL regime in which, even though the system does thermalize eventually, on short enough experimental timescales, it can exhibit the dynamics of a true MBL phase. So, okay, so as I said, we need strong enough disorder, but also the precise role of the range of interactions for the existence of MBL was questioned or under debate. So this is a question also that we addressed. And there is a lot of interest also in the understanding precisely how do the dynamics of glasses and many-body localization differ. And as I already mentioned, people are now focused also on open quantum systems. So again, these are all the questions that we have addressed in our work and that I will briefly discuss.
So Dragana, I am not at all in this field, but what I have heard is that skeptics are mentioning that to see many-body localization, you should switch off phonons, which is unrealistic.
That's coming. No, it isn't. Okay, of course it's coming, yeah. Okay, so most of the work has been theoretical. Of course, there have been some experiments. MBL has been reported in these synthetic many-body systems, which, yes, are well isolated thermally from the environment. Most of these were 1D, but MBL has been reported in 2D systems, in particular in ultra-cold atoms in 2D optical lattices. And this is actually the first such report. So what they do, or what they did, they prepared this 2D lattice, and at time equals 0, they can remove the atoms from one side of the sample of their system. And then they can measure the difference in the density between left and right sides as a function of time. So they measured the imbalance between the two sides as a function of time, and they were also able to vary the disorder. So in the case of 0 disorder, which corresponds to these green symbols, you can see that this imbalance drops rapidly to 0. In other words, the density becomes uniform very rapidly. But as you increase the disorder, you can see that this imbalance persists for a long time, and this was taken as evidence of many-body localization. So this is all very, yes.
Disorder here is just simply disorder in the periodic lattice that they create.
I think so, but yeah, I don't know to recall the details, but yeah.
Yeah. Seem to have a spectral potential there, the disordered laser potential at the bottom.
Yeah, I should have to, yeah, you're probably right. Okay, so so this is all very nice, but one problem for the interpretation, at least some of the experiments, is that, these systems are relatively small, typically small. The largest ones actually go up to 10,000 atoms. So in other words, they're very far from the thermodynamic limit where theorists make their calculations. And even though these systems are well isolated from the environment, Nevertheless, there is always some residual coupling to the rest of the world. So, and eventually the system does thermalize even here because of that. And I think the longest time scale for this MBL to survive in these systems is about a millisecond. So it is obviously, oops, oh, okay. I also wanted to mention that they investigated in this system, these ultra-cold atoms, the effect of the coupling to the bath. They could not reduce it further, but they were able to increase it. So when they do this on purpose, they found that the system does indeed thermalize much faster when the coupling to the rest of the world is increased. And in fact, this strong sensitivity of MBL to coupling to thermal bath is a key experimental signature of MBL. And this is in contrast to glassy systems, which are robust with respect to the coupling to the environment. So obviously, it would be desirable to study this in electronic, systems because they're much closer to a thermodynamic limit, and theorists would love that. But as Cameron pointed out, this has been a challenge to do because it is difficult to isolate electronic systems from the bath because of the electron-phonon coupling. Fortunately, we have silicon. Okay, so our experiments have been performed on the system that has been studied for many decades. This is it's actually the first system in which 2D behavior of electrons was demonstrated. So the 2D layer is formed on the silicon side of the silicon dioxide interface. So this is a silicon metal oxide semiconductor field effect transistor. And so at low enough temperatures, the electron move just in a plane. We have a 2D system. And the origin of this solder are the positively charged sodium ions that are randomly distributed throughout the oxide, and they're frozen at low temperatures. They're spatially separated from the 2D layer. So what the electrons feel is this smooth random potential. So we have this order. Now the important point for MBL is something that has been known for a long time, is that electron-phonon coupling in the silicon is very weak, including coupling between the 2D layer to phonons in the silicon. And at low enough temperatures, in practice, in the regime of interest, say temperatures below 2 Kelvin, which is not very low, the heat transfer from the 2D layer to the rest of the world is by diffusion through these contacts called source and drain, and up the measurement leads or wires that go through your cryostat. And if you put the system under a vacuum, then this coupling is reduced even further. And actually, this has been a problem for people who actually wanted to cool their electrons to that temperature. But this works to our advantage.
Just your 2D electron gas is, so SiO2, is it quartz or silica? Is it amorphous or is it?
It's amorphous, silicon, yeah.
And so you put, the dopants are this sodium gas.
No, okay, they're not really dopants. I mean, you don't dope them, they're just there, they're unavoidable in the fabrication.
So what brings mobile electrons?
Sorry? Oh, okay. All right.
Gating.
Yes, exactly. So exactly. So we have the gate. So there is this metallic electrode on the top. We apply voltage. We have there is also bandwidth, but okay. So we can change the carrier density by changing this voltage, and know that this is a capacitor, metal oxide. A 2D layer is another plate of the capacitor. So by changing the voltage, we can actually change the total carrier density in a 2D layer instantaneously within our experimental resolution, so time resolution. So it's an instantaneous process. So in other words, by changing the density, we are changing a parameter in the Hamiltonian. We're not injecting energy. We are just making a perturbation, and we'll be looking at the response. So I'll be focusing on this quantum quench protocol. And we can change the density by huge amounts. So the system can be prepared easily far from equilibrium. We can study the dynamics at different densities, ranging from the high densities where the transport is metallic to the low density regime through the metal insulated transition. So we had two sets of samples, both of, they were fabricated instantaneously, simultaneously, not instantaneously, simultaneously. So all the fabrication steps, and there are more than 100 of them, that are identical, except for the thickness of the oxide. So if there is, so these samples had, for MOSFETs, a relatively strong disorder. And again, the only difference is in the thickness of the oxide. So in one set of devices, the oxide thickness was such that the interaction between electrons in 2D layer is just 1/r. But in another set of devices, the oxide was closer to the 2D layer, closer than the mean electron separation in the regime of interest. So the gate screens the long-range part of the Coulomb interaction, and the Coulomb interaction is reduced to this dipolar form. So these are things that have been known really for decades. So we are going to study the dynamics in both of these to look at the range of the interaction. So if there are any differences in what we see, they must be due to the difference in the range of the interaction. Okay, so of course, before you study far from equilibrium dynamics, you need to characterize the ground state properties. I don't have time to show the data. This is just a sketch of the phase diagram that we determine in both sets of devices. As a function, so this is temperature, carrier density. At low enough densities, you find the exponential localization in the zero temperature limit, conductivity 0, which is the definition of an insulator. A density is above this critical density. This is where metal insulator transition occurs. We find this not Fermi liquid temperature dependence, but in the zero temperature limit, conductivity is finite, which is the definition of a metal, but it's very small. It's smaller orders of magnitude than E squared over H. So everything that I will be discussing today happens in a regime where the electron mean free path becomes smaller than the Fermi wavelength. So this is a regime where effects of disorder start to be especially important. Okay, so I think I can move on to the dynamics. And as I said, I'll focus on only one protocol, which is shown here in the bottom panel. You may not want to read the details of the protocol. Protocol is very simple. And I'll start with a case of a long-range Coulomb interaction. So basically, you start with a system at high density. You cool it down to your measurement temperature. And then at some point, time equals 0, you reduce the density or the gate voltage by a large amount. And all the time you track the conductivity as a function of time. So we can see at time equals 0, there is a big drop of the conductivity because we reduce the density, but it doesn't stop at this equilibrium value corresponding to the new density. It overshoots it in this case by orders of magnitude, and only at a much later time, note that these are hours, it approaches the equilibrium value. And we check that this is equilibrium by warming the system up to high temperature at this density. We don't change it, cool it back down again, and indeed, we waited long enough. So note that this is a huge perturbation. A change in the Fermi energy is comparable to the Fermi energy. So the system is far from equilibrium. So now you can repeat these measurements for different measurements at different measurement temperatures. You get a bunch of curves that are shown here. So here we are actually showing conductivity normalized by the equilibrium value corresponding to that temperature. In other words, on this log scale, this 0 corresponds to the equilibrium conductivity for each of these curves. So you can see as you reduce the temperature, this conductivity, which, as I said, overshoots this equilibrium value, goes farther, it goes away from equilibrium, but eventually turns back up. But as you reduce the temperature further, this minimum even falls out of our experimental time window. So we see this before this upturn, these non-exponential relaxations that we showed can be all collapsed onto the same function, which is a product of a power law and a stretched exponential, both of which indicate that there is a broad distribution of relaxation times in the system, which is what you expect in glasses. And in fact, in the zero temperature limit, this is reduced to a pure power law form, which is, again, you expect a power law in the vicinity of this phase transition. So this suggests a glass transition at zero temperature. Now, if we focus on what happens at longer times, as we, to look at how the system approaches equilibrium, it turns out, oh yeah, I do want to say that it's remarkable that this is, exactly the same dynamical scaling was obtained in spin glasses above glass transition temperature. So, okay, so now let's see what happens as you approach thermal equilibrium. It turns out that this is a simple exponential process, so you can extract the thermalization time as a function of temperature. And we see that it diverges in the zero temperature limit, which again tells us that the system freezes, strictly speaking, only at zero temperature. We have a zero temperature glass transition, which is not surprising, it's a 2D system. So even though at finite temperatures we don't have a true glass transition, on experimental timescales it's glassy. And if you calculate this thermalization time at 1 Kelvin, it turns out that it's orders of magnitude longer than the age of the universe. So for all practical purposes, we don't care that there is no true glass transition at a finite temperature here. Okay, so all right. So in addition, to this, obviously over the years we performed various protocols. As I said, we probed the response, other properties, correlations, and so on. Everything is consistent. So basically, what we find in the dynamics is that there is a well-defined glass transition density below which we have a glass transition at zero temperature for all densities. So this insulating phase is glassy. And we have this intermediate phase, bed metal phase, which also exhibits glassy dynamics, although there are some differences there. Okay, and again, the origin of this glassiness is the frustration in the system. We have a long-range cooling interaction, and we have disorder. So you may want to ask, does this glassiness require long-range interactions? Can it exist if the interactions are short-range? And this was actually our motivating question for studying the effect of the range of the interaction. But remember that our system is very well isolated from the environment, unless I tell you otherwise. Okay, so now we repeat the same protocol in this system with a short range or dipolar cooling interaction. Again, we cool the system down to the measurement temperature. At time equals 0, we perform our quench, monitor conductivity drops, overshoots this equilibrium value. And as we can see in the inset, again, it takes it hours to reach the equilibrium value. So again, you repeat this many temperatures, densities. So I'm not going to show that. I'll just again emphasize that this was a very large perturbation. The system was prepared far from equilibrium. So we want to compare the two types, the effect of the range of the interaction. Okay, so this is a long-range case, just an example of these relaxations. Yes.
Before you do that, I'm still wondering about the previous set of data. You showed the relaxation and how it scales with the relaxation time.
Yes.
And the minimum, on the other hand, do you understand why it shifts with lower temperature to
everything becomes slower. So as a function, as we reduce the temperature, everything is slower. So this is slower. It takes a long time for system to thermalize.
Yeah, I understand the time part, but the magnitude is a little surprising, isn't it, when you lower the temperature?
Yeah, but we are approaching
overshoot bigger and bigger.
Yes. Okay, so we do not actually understand the origin of the overshoot up to this day, and I will come back to that actually near the end of the talk. And I will talk about that. Okay, so let's see. Okay, so we want to compare. So again, this is a long-range case just for a different density. I already explained what happens here. Now for the same density in the system with a short-range interaction, this is what we get for different temperatures. I think even if you don't know anything about what these figures represent, you can see that qualitatively they are very different. For example, at intermediate times, we do not see this non-exponential dependence on time, but initially the relaxation is negligible, although the noise is bigger, both of which are expected in the case of MBL. But we do not see at intermediate times any evidence of glassiness like we did here. But I think the most striking feature or difference is what happens at long times. Here we had this temperature-dependent thermalization time, But here, all of these curves seem to reach equilibrium at about the same time. So we analyzed, we determined these times for different temperatures and densities. This is what we got. We did not see any systematic dependence. Yes.
Maybe this is going ahead on your talk, but those, I mean, what you call noise, is that actual noise or is this?
Yes. And
how do you know that for sure? I mean, because the noise is increasing with decreasing temperature. Could universal conductance fluctuations play a role here?
No, I think because that's that's what you expect in good metals, but not here. And in the MBL case, people do expect higher noise. One reason you can say because the interaction is shorter range, so there is less averaging, or the electrons don't know what's happening over there. There are other possible reasons that I'll mention later. And there are also some interesting or strange things that actually some of this noise, if you repeat the measurement some other day under the same conditions, some of the features seem reproducible, which is weird.
That would be universal conductance fluctuation. As far as I understand.
Okay, I don't see how that we can discuss it later. I don't see how that would fit, in this picture or in this regime where we are. But yeah, I mean, I'd like to know what's going on, of course.
There is no magnetic field here.
No, not yet.
It's also a microscopic sample. I mean, the length, the size of your sample.
The length is about 2 microns typically. Yeah, 2 microns. Yeah, but we've seen, as we discussed earlier, UCFs in samples, other materials, or millimeter size samples. So, okay, so we don't know. So anyway, we see the data are scattered around the same value, about 10,000 seconds. So each data point is 1 day of measurements. So what's going on? We have slow relaxation. It is not glassy. What is it? We recall that the system is well isolated from the environment. MBL should be sensitive to the coupling to the bath. And just like the cold atoms people, we could not reduce it further, but we could make it stronger. So we repeated some of these measurements with samples immersed in like helium vapor. These are these blue symbols, and we found that this thermalization time was reduced by an order of magnitude, which is what you expect. So in MBL. So these measurements were done at temperatures below 2 Kelvin, where electron-phonon coupling is still weak. We also performed some measurements at high temperatures where coupling to phonons becomes important, and there the thermalization time is reduced by at least another order of magnitude. So this strong dependence of thermalization time on the coupling strength, as I said before, is a key signature of MBL. From here, we are not able to depend the exact dependence on the coupling, but we see obviously that it's very strong, and it's also very different compared to what happens in the glassy case. As I said, you don't expect the glassy behavior to be sensitive to that, and we did, in fact, measure glassy dynamics even at higher temperatures where phonons are important, but there is no change in the dynamics of glasses because thermal fluctuation will just let the system explore this rugged free energy landscape further. So there will be really no change. Okay, so what we established basically is this dependence of the dynamics on the range of the cooling interaction. And at this point, I do want to acknowledge my collaborators, in particular Lily Stanley, a former graduate student. This was really, I think, really major work. So our study also addressed this question about the effect of the range of the interaction that was under debate. This particular case, alpha is the exponent, the power law of the interaction. There are many theoretical papers in the literature where they discuss various power laws, various models, whether MBL can persist or not. So anyway, we address this regime and the dimensionality of the system. So we can. So how does this compare to the experiments on cold atoms? They had a system that was an insulator, multi-insulator. They changed the density. We have a system that actually conducts, so it's in a way complementary to previous studies. And we changed the total density, as I said, instantaneously because it's a capacitor. But this does not necessarily, I mean, if it's MBL, then the electron density should also take a long time to thermalize. But the fact that total density has changed instantaneously doesn't mean that electrons have thermalized in the sample. There may be probably local rearrangements. And in these devices, we cannot use local probes to the best of my knowledge. So as a result of these local density rearrangements, while one would expect also to see large noise. And we do see, as you already saw, large non-Gaussian noise, which in the insulating regime in particular dominates. You can see here, you cannot see any relaxation or, I mean, everything is dominated by the noise. So maybe some of the noise has to do with these rearrangements. Maybe it's due to the particular realization of disorder. We actually do have some data, this is not published, where we change the realization of the disorder by warming up to very high temperature, room temperature, repeated the measurement, and then this reproducible noise features, not all of it, but that disappeared. So this is why I think, it's probably related to that. Okay, so what I showed you is that, in this 2D electron system in silicon at low densities, the dynamics is always slow, but the precise nature of the dynamics depends on the range of the interaction. So glassiness does require a long-range interaction. It does not persist. It does not exist when the interaction is short range, but if the system is well isolated, it exhibits MBL. So I hope I convinced you that we established a new solid state platform for studies of thermalization MBL in large systems on very long time scales. And this figure actually, what it shows is the initial conductivity after the quench for different densities at a low temperature. So you can see for all these densities you observe, this is the MBL case. We see the overshooting, except sometimes in the insulating regime. Okay, and I will come back to the overshooting again. So we do not understand the origin, but this is what happens. And what is interesting, I think, is that this MBL dynamics is observed just above the metal insulator transition. This is where the effect is most pronounced. And I don't know why. Okay, so now let me spend just a few minutes on the most recent data where we study this system that exhibit MBL, and now we want to open it. It's not well isolated anymore. We want to open it slightly. Before we couldn't, we did it in the kind of big step by introducing, helium gas into the, to surround the sample. So how do we open this system? Well, okay, so we can do it with a back gate. The device also has a gate at the back on the substrate. And so normally everything we've done so far and discussed was done in this configuration where electrons occupy only the ground subend. So they move, parallel to the interface. So we have this 2D system. But there are also higher lying subends. So by applying this backgate bias, you can reduce the subend splitting and between these two subends. And in systems that have a sufficient amount of disorder, each of these subends will develop a band tail of localized states. So we can apply this backgate bias such that some of these localized states are brought to below the Fermi energy, and they can also become populated or especially singly occupied because of the large on-site cooling interaction. So anyway, this has been known for a long time. So this is what we are going to do next. We are going to introduce a finite reservoir of these disorder-induced localized states. So it's maybe like having some metallic grains or quantum dots where electrons can also go. So before, again, I describe, just show you a few main results about the auto-equilibrium dynamics. Again, you have to characterize the ground state properties. I'm not going to go into details. You measure conductivity as a function of temperature. And we find, for different densities, we find behavior that is consistent with the previous studies where we observed, where we had these, these localized states from the upper subband also present and occupied, and we can determine from the temperature dependence the critical density for the metal insulator transition. In this case, the 2D layer is slightly farther away from the interface, so effective disorder is slightly smaller, which explains this. Oops, slightly reduce the, I'm sorry, slightly reduce the, it's not going back. Why isn't it going back? Okay. Reduce the critical density for the metal insulator transition. We determine the critical exponents. So everything is consistent with previous studies. We know that, this is what we have. So now we want to repeat again the same protocol. And here is an example of what we found for one particular density. Again, we perform this big quench, apply large perturbation, reduce the density to this value. And here are some of the curves that we measured at different temperatures. So we see this overshooting of this equilibrium value, but you can see that this thermalization time depends actually on the temperature. And this can be seen more clearly, maybe at least it's prettier from this color map. So these are exactly the same data. So we can see that the thermalization time, this light blue value corresponds to 1 to the equilibrium value. We can see that as we increase the temperature of this small range, the thermalization time changes by orders of magnitude. You can also do fits and, just a 2D fit and confirm this. So we are able now to actually see the temperature dependence of MBL in this case. So we also perform measurements at higher temperatures, additional temperatures. So I'm going to show you more data for this same density. Okay, so we see that in certain situations now, we don't see overshooting. These curves are coming from above. So it turns out that the temperature dependence is non-monotonic. So as we increase the temperature, these curves approach this value of 1. So you think, oh, they are reached equilibrium. But as you increase the temperature further, they start approaching from above. And you increase the temperature further, then they finally reach equilibrium. So what's going on? And, we have obviously hundreds of such measurements. We've done it again for different densities and temperature, and we are able to create a dynamical phase diagram as a function of temperature and density. So these are the latest data. As I've labeled here, the dashed lines are guides to the eye. So this purple region is a region where we observe this overshooting. And then we have this region that surrounds it, where there is no overshooting. We still see the same type of relaxation. And then at higher temperatures and densities, the system is in thermal equilibrium. Why? So we've identified, we reveal some intermediate regime as we approach the thermalization, which I think, there are, different theoretical models that discuss some kind of intermediate regime, but we don't know why this looks like this, and in particular, why this MBL region is surrounded. We actually checked that, here, the data here do not exhibit this overshooting. So, okay, so this is strange. If anyone has any suggestions or ideas, let us know. And this was the work of Charuni Visanayaki, who is a postdoc. We also looked at, for example, thermalization time as a function of density along these lines at a fixed temperature. And again, you see as you increase the density, this thermalization time decreases by more than order of magnitude, eventually vanishes. So this is not surprising. We have, moving towards the metallic regime. So the system is supposed to, does reach thermal equilibrium. Nothing strange happens at higher densities or temperatures. Okay, so do I have any time left to just to mention one slide that I can skip. Okay. Anyway, I'm not going to describe any data. I just want to say that we also addressed the question about the difference between GLASI and MBL by using different protocols. These are actually all unpublished results. And for example, there are some theoretical models for MBL that predicted some similarities to GLASI, such as a broad distribution of relaxation times, some hierarchies of time scales, dynamical heterogeneities. So one type of study that we performed is the study of the fluctuations, which gives you information about correlations. So this was performed after cooling. So we do not change the density here. We did see some similarities to GLASI dynamics, but when you look at, say, higher order statistics of the fluctuations, we do not find scale-free behavior that is characteristic of GLASI, this hierarchical tree-like structure that I mentioned at the beginning of the talk. And also more recently, this is still actually ongoing, we wanted to see whether MBL exhibits a breaking of time translation invariance like GLASIs do. So what does this mean? It means that, what's the aging or breaking of this time translation invariance? It means that the properties of the system depend not only on the time when you measure them, but also on how the system was prepared, on its age, for example, in the GLASI case, if it's older, it's slower, and so on. So we checked for that. So far, we have not seen evidence for the so-called full aging, but as I said, this is still ongoing. Okay, so to summarize, this I think is really, this system is an excellent platform for studies of far from equilibrium dynamics in large systems. We've seen two types of non-trivial out of equilibrium behavior, far from equilibrium. And we are able to vary the range of interactions, disorder, dissipation to a certain extent, but we cannot reach, there are regimes that we cannot reach with this device. So in order to perform further studies, it would be desirable to study systems that are more tunable, such as graphene-based devices, for example, and which could allow us to reach regimes that are previously inaccessible, in particular, a regime of strong disorder and strong correlations. This is a regime in which even the ground state or equilibrium properties are not understood, neither theoretically or experimentally. So one, of course, major theme would be to study various metal insulator transitions in these systems, and of course, far from equilibrium dynamics. And such devices, in principle, should also make it possible to use some local probes, such as STM, to actually see what happens in the sample as it tries to thermalize. So this is all I wanted to say today, and I thank you very much for listening.
You said like you have fluctuation data. Is that also time resolved? Like, do you have fluctuation?
Yeah, I mean, it's the same measurement, just a different protocol. You don't change the density, just cool the system down, measure conductivity as a function of time, and then you do statistical analysis. You know, look at the power spectra, fourth order statistics.
Because you of course mentioned that the fluctuation dissipation relations will not apply.
Yeah. Right.
So, but can you see that as you go close to thermalization?
You know, this was shown experimentally in spin glasses. It took many years and a lot of effort. I think this was done also. I don't know if you remember him. Here in Paris, I think. Anyway, it was very difficult to show, but yes, they were able to show it, but in the system it was kind of closer, not as far from equilibrium. And yeah, so we have not tried to do this. I expect that it would be even more challenging.
Yeah, I'm just wondering that as you go close to thermal equilibrium, does fluctuation dissipation relations start to?
Yeah, no, I mean, that's a great point, but we haven't reached that stage yet. So, I mean, this is really brand new. We are still, we just finished adding the data points to the phase diagram, but there are other things to check. And yeah, but thank you for the comment. We'll definitely keep that in mind.
I think in glasses you have a kind of effective temperature, fluctuation, dissipation.
This is true, but only when you're not very far from equilibrium. If you're far, it doesn't work.
More was like, can we use it as a probe of thermalization, that the actual fluctuation dissipation reaction?
Oh yeah, I think, well, yeah. But as Anu said, yeah, in the glassy case, when you're not too far, it works with some effective temperature. So this was done by Leticia Cuyandolo and Jorge Curchan at Sorbonne. Yeah.
I have two experimental questions. First, so very impressive, this difference between these two samples. But if I understand correctly, the thickness is different by a factor of 5?
One was 7 nanometers, the other one was 50. Yeah.
So question, can you have samples in between? And why don't you see how does it evolve? Because you see, my understanding, of course, you said it's short range, long range, very well, but there is this crossover, it's a fuzzy crossover.
No, okay, I don't think it's fuzzy because the difference is right.
Exactly.
Yeah.
So this is why. Is there a phase transition as a function of thickness?
Okay, so again, to fabricate these devices, this was done at IBM. You need a huge facility, and anyway, it's not possible anymore.
Okay.
But this is why we want to, another reason why we want to work on graphene-based devices, because then you can do all this.
So the second experimental question is the question of temperature. You see, I guess you measure the temperature of the substrate. And of course, your electrons, because you are not thermalized. So my question is, how can you trust this temperature measured as of course.
I didn't say this was an electron temperature, the temperature of the bath.
So my question is there any way to have an access to, actually, I don't know if temperature for electrons in this situation has any meaning, because you see there is no thermalization. So actually the temperature has breakdown. Now the question is, can you use noise when you are at least at the metallic as a thermometer? You see, have you tried
to do noise using
thermometer? Yeah, and you see, because
using what?
The noise of your conductivity, the spectral noise as a thermometer of the electrons.
Yes, that has been suggested. So normally you want to look at the Johnson noise. To do that, what we find here is 1 over F noise, 1 over F type noise. So so no.
If you go to high enough frequency, you would be in the range where you're not dominated by 1 over F noise.
Yes, but then we're limited by the setup, by the there is a cutoff due to the wire's capacitance and sample resistance, which is large. So there is a relatively low frequency cutoff. We cannot do that.
Okay, we can fix this. We can discuss later.
Okay, all right. Come to my lab to fix it.
I can wait.
Well, you can ask.
More questions?
Well, maybe I had the question. Again, as in spin glasses, you could imagine the difference between field cooled and zero field cooled. For you, this means either cooling first and changing the gate voltage then next, or the other way around. So do you see that kind of?
In the glassy case, yes. And this is one of the first things we saw. And that time, the postdoc who was working on this every day, she was coming, there is something weird going on. So yes, it's the first thing we saw, we observed, and then we decided to perform all these systematic studies. So, but yes.
So the undershoot is still present?
It's a different protocol. Basically, if you do this, you end up with a different value of conductivity, which keeps changing with time. So you don't know what in this measurement, what is the equilibrium value. So the way we determine equilibrium, we start from high temperature, just cool down to the measurement temperature at a given density, average over some time. Normally do not see any relaxations, you see fluctuations, but the average doesn't change. So so this is why we cannot just say sweep the gate voltage to measure conductivity as a function of density. Each data point requires warming the system up, cooling back down. So this last study that I showed in last few slides, this look at 2 years of measurements.
Any other questions? If not, let's thank Dragana again.